just looking and off-putting if you don't know what the whole story is going to be. What is an ordered field defined to be? It's a field together with some non-empty set of positive numbers. So you just abstract away the notion of positivity. Any field where you can make sense of what positive means is an ordered field. So if you've taken like abstract algebra, think about all the fields you know. If you can make sense of what positive means in that field, then it's probably ordered. Subject to some conditions. If you have two positive numbers and you add them together or multiply them together, you should still have a positive number. The trichotomy law says that for any element of the ordered field, there are exactly three things that might happen. One of them has to happen. No two of them happen. Exactly one of these three things happens. A is positive, A is negative, so negative A is positive, or A is 0. And that's like off-putting because that just tells you what positive means. You want to know what inequality means. But if you know what positive means, you know what inequality means. Any two elements of an ordered field, x is less than y should just mean the bigger one minus the littler one is positive. So you can make sense of all of the things about ordered field in terms of those axioms. And we made some progress into some things that should be true for inequality. If you add something to both sides of an inequality, you still have inequality. So now I'm like just recalling the theorem we proved some of. Transitivity. No, different variable names, whatever. If x is less than y is less than z, then x is less than z. The trichotomy law for inequalities. If you have any two elements of the ordered field, either one is bigger than the other, or the other is bigger than the one, or they're equal. And this is actually going to be something, like, it feels obvious, but it's going to be important. That means that if you, as an analyst, want to show two things are equal, you don't need to show they're equal. You just need to show that one is not less than the other, and the other is not less than the one. You can show those two things, they have to be the same. And then finally, if you multiply both sides of an inequality by a positive, you resolve the inequality. And there are two other rules written there. And if I recall right, we proved like the first two of the items in the list. And I think the trichotomy one is worth doing just because there's some novel logic in it. So, let's try to prove the trichotomy law. So I'm going to pick up right here. So let's start by getting an idea of how we should proceed. So, we better start by considering any two elements of this field, A and B. We need to prove that exactly one of those things is true. So what's our goal? Is exactly one of A is less than B is less than A, or A equals B is true. And whenever you want to prove that exactly one of some things happens, here's a good way to go about it. At least one of these things happens. No, two of these things happen at the same time. That would do it, right? Yeah, and like, I don't know, you've had occasion in the past to like prove that some equation has exactly one solution. How do you do that? You find one solution, or you show that there is one, and then you show that there aren't two. We'll do the same thing here, except we have statements. We want to show that exactly one of them is true. So let's try to parse it out. A is less than B, what would that mean?
That B minus A is positive.
So this translates to and from B minus A is positive. What about that one?
A minus B.
And the last one? Oh, I guess that's a state equals B. Ooh, let's say it a different way. How about B minus A equals 0? Does that look an awful lot like the trichotomy law that we assume about the positive numbers? Ah, there's the proof technique. So let's use that. So now I'll come into this. So consider any A and B in this ordered field. By the trichotomy law, exactly one of the following things holds. Either B minus A is a positive number, or negative B minus A is a positive number, or B minus A equals 0. So exactly one of those three things holds. Right now I'm going to try to show that at least one of these things holds. So in case one, which one of those things holds? B minus A in P means B is greater than A. And like that second line, negative B minus A is in P, that looks complicated looking. But like, you know what to do, distribute the negative sign because we have a distributive law even for negative signs. What does it become?
A is greater than B.
Better be A is greater than B? Yeah. And notice, I'm playing fast and loose with like the field axioms now. I'm not saying which ones I'm using, and I won't in general from now on. And finally, B minus A equals 0. What does that translate to?
A could be.
Nice. So, what have we proven now? We have proven that for any A and B in an ordered field, at least one of those three things happens. If 1 happens, then B is less than A. If 2 happens, then A is bigger than B. If 3 happens, then A equals B. We're halfway done. Next, we want to show that 2 of these things don't happen simultaneously. So let's proceed by contradiction. Let's suppose that 2 of these things are simultaneously true. In each case, we'll get a contradiction. So suppose that 2 of these conditions hold for the sake of contradiction. If those 2 hold, if A is less than B and B is, what? Yeah. Don't want to say the exact same thing twice. If both of those things happen, then let's get a contradiction by going back to the trichotomy law. A is less than B, what does that mean? B minus A is positive. What about the other one? A minus B is positive. And this is almost a contradiction. In fact, it is a contradiction, right? But like, the actual statement of trichotomy law has a negative sign out front, so let's pull that negative sign out front. Ooh, so that means B minus A and negative B minus A are each in P. That contradicts the trichotomy law. So that couldn't be the case. There are like 2 other cases that you need to get contradictions in, right? Do you think you could just like say the exact same words almost and get the contradictions you need? Proof in all the other cases is identical. Groovy. Feel pretty good? And see how like there'd be a whole lot of redundancy in this proof if I did all the cases. So like, do them in your head, tell the reader to do it in their head. If the reader needs to check them and they don't think it walks, then you're in trouble. Cool, we feeling good? All right, last thing I want to do in this packet is we're going to prove some stuff about what happens when you raise an element of a field to a power. And you know what, I think I'm going to read this slightly out of order. Let's state the theorem, then we'll remember what powers mean, and then we'll jump down to how you would even prove such a claim. So, let x be an f, n be a natural number. If x is bigger than 1, then how should 1 compare to any power of x? If you take a number like 7 and keep raising it to a power, it's going to keep getting bigger. always be bigger than 1. If you start with a number that's between 0 and 1, how should 1 compare with powers of that? Yeah, right? If you take like 0.7 and square it, that's still less than 1. Multiply it by 0.7 again, it's still less than 1. And if you take 1 and raise it to any power, then the result is always equal to 1. All right, and that's obviously true, right? That's something that you know has to happen. But in order to prove it, we want like a definition. The definition is going to be something that we can actually walk with logically. So like, what does x to the n mean? You know kind of what it means. It means x times x times x times x n times. But like, what does it mean to multiply a thing by itself n times? Well, here's one way of making sense of it. It means you multiply it by itself n minus 1 times, and then you multiply by x again. That sounds like a recursive definition. So, here is a recursive definition of x to the n. Let f be a field. For any x and f and any natural number n, we define x to the n recursively by the rule that x to the 1 is x. So I'm just defining x upper 1 equals x. And if n is a natural number bigger than 1, then x to the n is defined to be x times x to the n minus 1. Fair enough? All right. And whenever you see a recursive definition and you want to prove something using that recursive definition, you should use induction. And this is like the false induction that appears in this set of notes. So how do people feel about induction? There are people who would say they feel positively about induction. And people would say they feel negatively about proving things using induction. Okay, well, there's something nice about it in that it's like very formulaic. Like once you know that you want to use induction, you get for free like the bite-sized pieces that you need to prove. And that's like nice when you can use it. So let's state the principle of mathematical induction. So proof technique. So let's let P of n be a statement which makes sense for every natural number n. So it's some statement that you can evaluate as true or false for every natural number. For instance, here's one statement. 3n minus 1 is even. Is that something that is either true or false no matter what natural number you plug in? Yeah, you can check if a natural number is even or odd. If two things happen, if P of 1 is true, and for every natural number n, P of n implies P of n plus 1 is true, then it follows that for every natural number n, P of n is true. That sound like induction to you? And what's the logic? Well, once you've proven P of 1 is true, great. Then once you've proven that P of n implies P of n plus 1 is true for every natural number n, well, since P of 1 is true, you know P of 2 is true. Oh, since P of 2 is true, you know P of 3 is true. Since P of 3 is true, you know P of 4 is true. So that kind of makes sense why this should mean that the statement is true for every natural number. If you want to prove that induction works, then what you really need to go back to are the axioms that govern the natural numbers. Just like we're doing the field axioms and stuff for the real numbers, there's a set of Peano axioms for the natural numbers. Induction follows from them. So that's like a lot of abstract stuff, but now let's be very concrete and explicit. Let's try to compose inductive proofs of these claims. So this means if you want to prove something using induction, you need to prove two things. You need to prove the statement is true for n equals 1. Next, you need to prove that if the statement is true for any fixed n, the statement is true for the next n. This all sounds familiar? All right. So that tells you some lines that you just have to include in an inductive proof. So let's suppose you want to prove this claim for every natural number n, 1 is equal to x to the n if x equals 1. Well, you better include a base case. So, in fact, what I would propose is your inductive proof should have base case, colon. We will show that, and then put the thing you're going to show in the blank. What do you need to show in the base case of this claim?
1 to the power of 1 equals 1.
And there's not like space there to prove it, but like now you have something really explicit to prove. Oftentimes the base case is pretty easy, because you're just proving a very explicit claim. Sometimes the base case is the hard part. Inductive step. So we need to prove this. So we better start by considering any natural number n. We then get to assume P of n is true. So what do you get to assume if you wanted to prove this statement by induction?
P of 1 is true.
Yeah, but I haven't written down what P of 1 is.
That 1 to the power of 1 is equal to 1.
Nice. Not 1 to the power 1. 1 to the power of n equals 1 for this fixed n. So what have I done? I've considered any natural number n, and I've assumed for that natural number, 1 to the n is equal to 1. What do I need to prove?
That it's still the same with n plus 1.
That it's still the same with n plus 1. But like, if you write that, then that's like really ambiguous and confusing. So you can write exactly what you mean as
1 to the power of n plus 1 is equal to 1.
cool. And if you include those sentences, then like you know what you need to prove. And knowing exactly what you need to prove in each step is sometimes half the battle. It's not always half the battle. Sometimes things are like hard beyond that. All right, so shall we do some induction? Let's do some induction. And I think I indicated here that I only want to prove one of these. The proof for all of them will be basically the same. Which one should we do? 1, 2, or 3? 2. Way to pick the one that's like probably the most complicated. It looks more complicated anyway, right? So let's do 2. I think I put space for each of them. Proof of claim 2. Let f be an ordered field, and 0 be less than x be less than 1. We will inductively prove that x to the n, let's even put this, 0 is less than x to the n is less than 1 for all n in n. It's nice to have a really strong reminder of what an on-off is we're going to show. So, I'm going to change the statement. Looks like I have the 0 is less than everywhere, so let's do that. Okay, we'll add that in. That's illegible. Is bigger than 0 is what I wrote. That's going to make it worse. All right. So, base case. We need to show that 0 is less than x to the power 1 is less than 1. And like, I don't know, let's just talk this through in words. Why should that be true?
Something less than 1 to the power of 1 is itself still less than 1.
Nice. By assumption, 0 is less than x is less than 1, x to the 1 equals 1, so x to the 1 equals x. What am I saying? So, 0 is less than x to the 1 is less than 1, completing the proof of the base case. And I really like this notation where you write in words exactly what you're going to prove at each stage. If you say something silly, let's assume for the sake of induction that n is true. I'm going to show that n plus 1 is true. That's nonsense. N is a natural number. It can't be true or false. 5 is true doesn't make sense. A particular statement is true for a fixed natural number does make sense. So you have to write out that statement. If you're doing your scratch work, I don't care what you write. I don't see your scratch work anyway. So let's do the inductive step now. So let's consider any natural number n. Let's assume that the thing we want to prove is true for that natural number n. We have to show that thing is true for the next natural number. So let's try to figure out why that is true. And there's space on the next page, but let's like write down some scratch walky thoughts in this space. So I guess we want to show two things, goals. 0 is less than x to the n plus 1. And I need x to the n plus 1 is less than 1. So how can you convince me that those are true?
So we know that x is positive, so like if you, by the axiom, that's like any number in P times any other number in P is also in P.
Nice. We know x is bigger than 0 and x to the n is bigger than 0 because of the inductive assumption. So we can even put that in terms of positive numbers. So x is in P and x to the n is in P, where P is the set of positive numbers. All right, and then what's the next thing you said?
I think it was good. I think I was trying to say that.
Well, you also said something about the product of two positive numbers, right?
Oh yeah, so you could split like x to the n plus 1, you can split that into x to the n times x to the 1, which is the axiom. Yeah.
Nice. And then you can translate that back into is bigger than 0. All right, so there's like half of the inductive step. Let's figure out how to get the other half. Let's start by just writing down the things that we get to know. So we know two things right now. We know x is less than 1. That's like the assumption. We also have the inductive assumption. So let's try to use those two things. And I tried to be helpful by putting things we know about inequality on the bar. So you don't even have to translate all the way back to P. Now, let's just start with this. What's x to the n plus 1 by definition?
X to the n times x to the 1.
X to the n times x to the 1. In fact, that's right, but I'm going to leave out the to the 1. It's not long to put it. In fact, you can put it if you want. I won't. All right.
And then because we know x is less than 1, x to the n is less than 1, their product is less than 1.
I like all of that except for the justification.
Okay.
So here's the issue. Is negative 1,000 less than 1?
Yeah.
Is negative 10,000 less than 1?
Yep.
Is their product less than 1? No. So you also need, you're multiplying by a positive number. So let's use that. Let's use the fact that one of them is positive. So let's see. That's less than x to the n times 1 as x to the n is bigger than 0 and x is less than 1. Okay, what can we do next to get all the way to less than 1? That's something just equal to x to the n, right? I know what my goal is. I want to show that this sucker is less than 1. If you can convince me that that thing is less than 1, then transitivity does the job. Why is x to the n less than 1?
Because of our assumption it's faulted.
That's less than 1 by the inductive assumption. In your Scratchwalk, you can abbreviate assumption however you want, but I'm going to try to avoid writing any swear words. Groovy. That seemed like a proof. Should we take the effort of putting that into WADs on the next page? Is that WAF time? Let's do it. So, we have the base case done. Let's do the inductive step. And we already have it typed, but I'm going to put it anyway because, like, I think the thing that makes me most upset when I read inductive proofs is when they're set up adequately. So, let's consider any n in n, and we will assume 0 is less than x to the n is less than 1. We will show 0 is less than x to the n plus 1 is less than 1. All right, now let's just put those things into WADs. So let's see. The fact that they were positive, the 0 is less than, just followed by the two things that are bigger than 0, right? As 0 is less than x, and 0 is less than x to the n, the closure of the set of positives under multiplication says 0 is less than x to the n times x, which is of course x to the n plus 1. So there's the is bigger than 0 part of the proof. And I know it's on the previous page, but so let's say it like this. On the other hand, because I'm showing another inequality, x to the n plus 1 is certainly x to the n times x. And what was the logic we used on the previous page? Yeah. Nice. And that was true since x is less than 1 and x to the n is bigger than 0. Finally, what did we do with x to the n times 1? Why is that less than 1?
Because x to the n is greater than 0.
I think it's just using, yeah. Since x to the n is less than 1 by the inductive assumption. And maybe the closing thing is by transitivity. X to the n plus 1 is less than 1. Nice. Is that what we wanted to show in the inductive step? Have we now shown that 0 is less than x to the 1 is less than 1? And have we shown that if 0 is less than x to the n is less than 1, then 0 is less than x to the n plus 1 is less than 1? I hope so. Oh, cool. By the principle of mathematical induction, then, for every natural number n, the thing we wanted to show is true. Cool. So hopefully this has been like a reasonably gentle reminder on like how to structure an inductive proof. When you want to prove something by induction, make sure to like break down and really explicitly say what you need to prove in each step. And then how you prove it is up to you. Probably you need to use the inductive assumption during your inductive step. In fact, if you go and use induction and find that you don't use the inductive assumption, then here's what you do. You erase all of your proof except the inductive step. Your inductive step is a direct proof. Now just tell me that. But don't actually just erase, like rewrite it. Neato. Folks feeling good? All right. So, as a reminder, I have pushed back this deadline. I'm going to correct Canvas when I get back up to my office to actually have the deadline be correct in Canvas. How many people have just already made a bunch of progress on these problems? All right, well, that's good. I mean, if you've made some progress that's well in advance now. I want to start in on, announcement. There's a challenge problem available now that is going to show you that there is another definition of an ordered field which is equivalent to the one you already have, namely a field with an order. Let's talk about absolute values. Right, this is going to be an analysis class. You remember, like, the definition of the derivative has an awful lot of absolute values in it. Definition of a limit has an awful lot of absolute values in it. So we're going to need absolute value like a lot. And here's a list of, well, let's start by remembering what absolute value even means. Absolute value has like a case-wise definition, right? And like, you know what I'm about to put in those blanks. If x is a number bigger than or equal to 0, then what's the absolute value of x?
Is that greater than it's x?
And in the other case?
Negative x.
Nice. Okay, cool. I don't need to linger so long on that as I do with my pre-calc class. It's really fun teaching analysis and pre-calc at the same time because I talk about the same topics, but in totally different ways. So we have this function called absolute value. The following are the important properties that this function has. And we'll only prove some of them. Let f be an ordered field and a and b be elements of f. Oh, notice, I need to be able to think about inequality to do absolute value. So this only makes sense in an ordered field. I need to have a sense of inequality. For any element of that ordered field, absolute value of that thing is bigger than or equal to 1. That seems true? The absolute value of a number equals 0 if and only if that number equals 0. Yeah, cool. Absolute value of a number equals absolute value of negative that number. Nice. For any number a, negative absolute a is less than or equal to a is less than or equal to absolute a. Maybe that seems more mysterious. But in fact, that's one of the ones we'll prove. So you're nodding your head I like that. What are you thinking? Yeah.
Why did I see that the middle part there had the absolute value of it?
Oh, okay, so you thought it didn't say anything meaningful at all, basically. So absolute value is like a case-wise function, right? So I think to prove something like that, cases are the way to go. I know there's an indication of what's going to be proven there, but let's try to think in terms of cases. So if we wanted to prove that, then when a is bigger than or equal to 0, what is it that we need to prove? If a is bigger than or equal to 0, I can replace all the absolute value of a as just a, right? If a is bigger than or equal to 0, then all I need to show is negative a, less than or equal to a, less than or equal to a. Is that true more or less obviously? Yeah, certainly a is less than or equal to a it's a truism. It's part of the or equal to. And a is positive, so the negative 1 is less than 0, so the positive 1 is bigger than 0. The other case is if a happens to be negative, we get negative a, less than or equal to a, less than or equal to negative a. I mean, it just looks more complicated now. If one of those two inequalities is obvious. It's double negative a is a. In fact, you proved that in the field axiom thing, right? That was one of the things you proved? Thought it was.
I think it's homework for you.
Yeah, that's what I meant. That's why I said you did it. I didn't do it. So this one's obvious. Oh, well, if a is negative, then negative a is positive. Positive numbers are bigger than negative numbers. Oh, so yeah, checks out. And that's basically the proof we'll give. The product of the absolute value of the product is the product of the absolute values. That checks out too? Yeah, I think so. if b is not equal to 0, then its absolute value is not equal to 0, and the absolute value of the inverse is the inverse of the absolute value. Absolute value a is less than or equal to b if and only if a is in between negative b and b. And finally, the triangle inequality. Whenever you see the absolute value of a sum, it's less than or equal to the sum of the absolute values. We will use the triangle inequality an awful lot in this class. And then there's a version 2 of the triangle inequality that says something similar with subtraction. So let's try to make some progress in these proofs. And I said in here that like my goal is 4, then 7, then 8, because triangle inequality is the most important one. The things I'll need to prove triangle inequality is 7. To prove 7, I'll use 4. So, I don't know, one of like 1 through 3, would you like to go through like sketching a proof for one of those first? Cool, yeah, case-wise. Prove it when A is positive, prove it when A is negative, then you're done. And 0. So, let's prove the triangle inequality. I wanted to start with proof with the claim for, which somehow we've already sketched, right? So, there are like 2 cases. Either A is bigger than or equal to 0 or it's less than or equal to 0. In each case, we have to conclude that negative absolute value of A less than or equal to A less than or equal to absolute A. So there's the thing we need to prove. There are 2 different cases. In the first case, you've already told me what I'm about to write, right? There's the thing I need to prove. If A is bigger than or equal to 0, absolute A is equal to A, and negative absolute value of A is equal to negative A. So the claimed inequality, the thing we need to show, and like, you've already convinced me it's true, so we're just going through the motions now. One of those 2 is obvious. First one or second one? Well, one of them's more obvious than the other.
Second.
Yeah, the second's like the most obvious, but it's a truism. Ooh, so the word truism is a word for a statement that is true just because of the wording. A is equal to A is a truism. To see the second inequality, A is bigger than or equal to 0, so negative A is less than or equal to 0. By transitivity, A is bigger than or equal to negative A. That completes the proof in case 1. Do you think we even need to go through the proof in case 2? Do we want to have things written down for case 2? Okay, then we will do. In case 2, A is less than 0. And otherwise, like, this space is like copy-paste what's above. So it's just filling in the blanks differently. If A is negative, then the absolute value of A is...
Negative A.
So the inequality we need to show is something is less than or equal to A is less than or equal to something. What goes in that blank? Negative, negative A is less than or equal to A is less than or equal to?
Negative A.
Perfect, yeah, I was going to screw that up. One of these is a truism. Which one?
The first one.
Nice. Since, I guess, negative A is equal to A. Cool. Feel good? All right. So I guess we need to convince ourselves why the other is true. And it's on the next page, but let's like sketch out why. So why should these 2 satisfy that inequality?
A should belong to negatives and negative A should belong to positives.
Nice. So A is negative, so it's less than 0. Negative A is positive. So it looks like transitivity with 0 does the job. To see the other inequality, notice that since A is in fact strictly less than 0, negative A is bigger than 0. So by transitivity, negative A is bigger than A. That completes the proof. Feel good? Yeah. Second one. Claim 7. Let F be an ordered field. Consider any A and B in F. We have to prove absolute value of A is less than or equal to B if and only if negative B is less than or equal to A is less than or equal to B. Feel good? So there are 2 different directions. This is an if and only if. So we need to prove if this, then that, and the other way around. And I don't know, let's again go and like off to the side and scratch walk this. So we get to assume absolute value of A is less than or equal to B. And our goal is those two inequalities. All right, well, let's just think in cases again. Either A is positive or it's negative, or 0. If A is positive, then what do we get? Then what does the assumption become?
That A is less than or equal to B.
Oh, cool. That's one of the things we wanted. So now you just need to convince me of the other one. Let's see, if A is known to be non-negative, then negative A is non-positive. It's less than or equal to 0. So if I need B more bigger than or equal to 0, why do we win? It's scratch walk, so it doesn't need to be, explained in detail. Oh, cool. So I just need B to be bigger than or equal to 0, but B is known to be bigger than or equal to A. Oh, what's the thing I know about absolute values? Bigger than or equal to 0. I guess that's one of the claims we didn't prove, but you all seem quite confident that they looked easy to prove. So let's use that. Since absolute value of A is bigger than or equal to 0, and B is bigger than or equal to A, then transitivity tells us B is bigger than or equal to 0. Now we'll actually do the case-wise attack. Or half of the case-wise attack. Since I started so late into this section, I'm not surprised that I didn't finish. It would have been really surprising if I had. In case 1, A is bigger than or equal to 0, absolute value of A is equal to A. So the assumption absolute value of A is less than or equal to B just becomes A is less than or equal to B. That's one of the two inequalities we needed to prove. So halfway there. To see the second, since B is bigger than or equal to 0, negative B is less than or equal to 0. And by assumption, we have 0 less than or equal to A. I don't really care about negative B being less than or equal to 0. Oh, no, I do. I do. Absolutely.
Do you want the other one to be reversed, that 0 is less A?
No, I think I'm happy, right? B is less than or equal to 0. 0 is less than or equal to A. Blah, 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 blah. There's my goal. So negative B is less than or equal to 0, less than or equal to A. Transitivity doesn't. Okay, so I got myself confused, but not about anything deep. Think case 2 is going to be pretty similar? All right. So the next time we meet will be Friday. So here's something that I think will be perfectly reasonable. I don't want to have to do case 2. You do case 2. If I can fill in those blanks, I think you can do that. People think that's reasonable enough? And in fact, if you want the rest of Friday to be like really pleasant and light, try to just complete the rest of the proofs in this page. And then once we're done with this, I'll start it on completeness. Nice. And if I fail to update these deadlines by like 1, and you start feeling like antsy that I'm not going to do it, you can send me an annoyed email saying, please do the thing. You don't even need to say please. Polite emails are nice. politeness of email is not a grade item in this class.